Okay, hello guys. This is Adjan Saeed, and we are going to resume our discussion for after midterm, starting with spectral theory and compact operators. If you remember, we already discussed the first 4 pages, so let me quickly recall what we said. If you remember, we talked about the bounded operators. Okay, bounded operators between normal spaces, in particular Banach spaces. And then we talk about this, if you remember, that linear operator is bounded if and only if it is continuous. Then we talk about operator norm, and if you remember, we talk about this theorem. And then if you remember, we said that the set B of X denotes the set of all bounded linear operator on a Banach space X, which is actually itself is a Banach space with operator norm. And even more than that, it's a Banach algebra with this product is given by composition, such that it has the submultiplicativity property. And then we talk about compact operators. We gave you the definition of a compact linear operator. And if you remember, we said that a compact linear operator is automatically bounded. And then this remark, and then if you remember, we talk about this theorem without proof, and we said that if we have a bounded linear operator between Banach spaces, such that the dimension of the range of T is finite, then T is compact, and the product of a compact operator with any bounded operator will be compact. Okay, when we say product, it means composition. So now we have to continue from here. A spectrum and resolvent. Okay, look at here. We said that B of X, the Banach space or the Banach algebra of all bounded linear operators on a Banach space X. This Banach algebra is unital. When we say unital, it means the product on B of X, which is given by composition, has identity element. And that identity element is identity operator. So we know that the composition or product of this identity operator, it means it maps every X to itself. So you know that the product or the composition of any operator with I, like T, Ti equals It equals T. Okay, so the identity operator is the unit element of B of X for product. Okay, like this. If I want to show you, this is easy to see, right? For any bounded linear operator, right, Ti equals It equals T, right? So this is the identity element. Okay, and we have a definition here. T to the power of 0 is defined to be the identity operator, and when we say T to the power of n, it means the product, which means the composition of T with itself n times. Okay, we have a definition here. Now look at here. A bounded linear operator on X is invertible if there is a bounded linear operator like S, another element in B of X, such that TS equals ST equals I, identity operator. So we know that from the linear algebra, let's say, this bounded linear operator as an operator, as a linear operator, is invertible. Algebraically is invertible. So let me repeat again. T is a bounded linear operator on X, but as a linear operator is algebraically invertible if it is injective and onto. But this is algebraically, so the algebraic inverse must be bounded also, because we are talking about the inverse of T in B of X. But the algebraic inverse, it means if T is injective and onto, so it has an algebraic inverse, let's say S. But this algebraic inverse S, by open mapping theorem, is automatically bounded. You can see here I mentioned. You can see if you are familiar with open mapping theorem. When we say bijective, look at here, the algebraic inverse of a bijective bounded linear operator T. It means T is a bounded linear operator. When we say bijective, it means T is injective and onto. So it has an inverse, but this inverse is algebraic inverse. But this algebraic inverse automatically is bounded by open mapping theorem. I don't know if you know about open mapping theorem or not, but anyway, so the algebraic inverse will be automatically bounded. So it means if T is algebraically invertible, it means that algebraic inverse will be automatically bounded. So it means T is invertible in B of X automatically. And you may refer to some functional analysis book to recall open mapping theorem. And look at here, if T is invertible, it means it has an inverse. So, and the inverse of T is denoted by T by this. And T inverse, it means the inverse of T is unique. We can prove that it is unique. It's easy, I leave it to you. And T inverse, which means the inverse of T is also invertible, and the inverse of T equals T itself. Another fact that is easy to check, that the product of two invertible operator is invertible. It means T and S are invertible. So TS is also invertible, and the inverse of TS is given by S inverse times T inverse, or S inverse T inverse. And we have an interesting fact here. Again, this is easy to prove that bx to the power of -1, or simply bx inverse, denotes the set of all invertible element of B of X. It means this, the set of all invertible operators in B of X is denoted by bx inverse. We can show that bx inverse is a group under multiplication or product, which is given by composition of operators. So we can show that bx inverse with the composition is a group. With the composition of the operator is a group. Next, look at here. We have an interesting theorem and very important. But before that, I don't know if you remember this fact from the complex analysis. At least you should be familiar with this from real analysis. But like what I'm saying is this: if you remember, we have this from complex analysis, that 1 minus z to the power of minus 1, which means 1 over 1 minus z, equals this power series sigma zn n from 0 to infinity. So now we have something similar to this for bounded linear operators, this proposition, which is very important and interesting. Now look at here. Okay, let me read the statement of the proposition. T is a bounded linear operator on X, okay, such that the norm of T is less than 1. Then I minus T, I is the identity operator. So I minus T as an element of P of X is invertible, okay, such that, look at here, the inverse of I minus T is given by this infinite power series. Look at here, when we say the sigma Tn n from 0 to infinity, this means, okay, t to the power of 0, which is I plus t squared, which means the limit of the partial sums, right? This is an infinite series. So the sum of this infinite series equals the limit of the partial sums. When we say sigma t to the power of k from 0 to n, this is the partial sum, okay? So this is the inverse of I minus t, and moreover, look at here, the norm of the inverse of I minus t, or we can say I minus t inverse, is less than 1 over, or 1 divided by 1 minus the norm of t. Okay, so let's check the proof. Look at here in the statement. Okay, first we have to show that this power series is convergent, okay? And look at here, when we want to show that this is convergent, okay, the sequence of partial sums, of this power series is a sequence in B of X. So when we want to show that this sequence is convergent in B of X with some topology or norm, right? So topology here is given by operator norm, okay? So look at here, you can see here, to do so, B of X is a complete space, right? So it is enough to see that the sequence of partial sums of this power series, which is this one. Look at here, Sn is the sigma tk, k from 0 to n. This is the sequence of partial sums. The sequence of partial sums is a sequence in B of X. If we show that Sn is convergent, then this is convergent. Since B of X is a complete space, it is enough to see that Sn is Cauchy, right? Okay. First of all, look at here, by the assumption, you can see here, the norm of t is less than 1, okay? And of course, greater than equals 0. Now look at this infinite power series. Sigma, the norm of t to the power of n, n from 0 to infinity. Since the norm of t is between 0 and 1, so this is actually a geometric series in R, right? It's convergent, if you remember from the real analysis from calculus. This is convergent. And this is convergent to what? To convergent to, because this is a geometric series, the first term of the series is 1, and the common ratio is the norm of t. So this is convergent to 1, the first term, right, divided by 1 minus the common ratio, which is the norm of t. Okay, so this series is convergent in R, right? So therefore it is Cauchy. When we say it's Cauchy, it means for any positive number like epsilon. Okay, there exists a positive integer like n such that for every n greater than m and m greater than equals n, the absolute value, it means the distance between these two, look at here, this is like actually Sn, this is Sm, look at here, yes, the absolute value of these two, and it is easy to see that, look at here, this is from 0 to n and this is from 0 to m, and n is greater than m. Okay, so this becomes sigma k from m plus 1 to n. Okay, this is easy to see, and we don't need to put absolute value because each term of the three is positive. So this is the absolute value of Sn minus Sm is less than epsilon, which is equal to this. Okay, because it is Cauchy. Now look at here. Okay, look at here. Yes. Okay, I just made a mistake here. I said Sn, Sm, but I mean Sn, the partial sums for this three, not this Sn. Okay, I just made a small mistake. When I here said Sn minus Sm, it means the partial sums for this power series, not this one. Okay, remember. Okay, it doesn't matter. Okay, now look at here. So for every n greater than m greater than equals n, the norm of Sn minus Sm equals, okay, this is Sn, okay, minus Sm, which is equals to this. Look at here, this is from 0 to n, this is from 0 to m, so only left k from m plus 1 to n, t to the power of k, and the norm of this sigma is less than sigma the norm of tk. Why do we have this? Why do we have this? This is true, this is true, this is less than this by the triangular property of the norm, right? By triangular property of the norm, right? If you remember, I'll just quickly remind you, we have in any norm space, right? In any norm space, we have the norm of here, the norm of a plus b is less than or equal norm of a plus the norm of b. Okay, so this is true by the triangular property of the norm. Okay, now here we have sigma, the norm of tk, is the finite sum, is less than or equals sigma the norm of t to the power of k. Okay, and to tell you this is less than epsilon. Okay, you can see why this is true from here, why this is true from here, and this one is less than epsilon. But why do we have this? Why this sum is less than this? Okay, this sum is less than this because of the submultiplicativity property. What I mean is this. Look at here. Do you remember the submultiplicativity? Let me remind you what was the submultiplicativity property. Okay, let me raise this. Okay, do you remember the submultiplicativity property that we said the norm of st, okay, the norm of st less than or equals the norm of s times the norm of t, right? This is submultiplicativity property. Okay, so when we say, look at here, when we say the norm of t to the power of k, right? What does it mean, this, the norm of t here? Look at here. the norm of t to the power of k. This means okay, the product of t k times, right? Look at here, I'm explaining here. Okay, this means the product of t k times, right? It means t times t. How many times? K times, right? K times. So now you apply this submultiplicativity property. So this is less than, look at here, this is less than the norm of t times the norm of t okay, here, norm of t and product the norm of t. So how many times? K times. So the norm of t, k times. So this becomes actually the norm of, this is actually the norm of t to the power of k. Correct or not? So you can see the norm of t to the power of k is less than the norm of t, k less than the norm of t to the power of k. You can see here. So this is true by submultiplicativity, and this one is less than epsilon. Okay. So this shows that Sn is Cauchy, right? So Sn is the sequence of partial sums of this power series. So it means this series is convergent, right? When we say it's convergent, the sequence of partial sums of this series is a sequence in B of x. So it is convergent in B of x. So it means it is convergent to an element like S in B of x. Okay. So it means this, let's say S is sigma Tn n from 0 to infinity, because S is the limit of this series. Okay. Now we want to show that, okay, look at here, if you look at the proposition, we want to show that this series is the inverse of I minus t, right? So we have to prove that I minus t times S equals S times I minus t equals identity operator, okay? Which means that S is the inverse of I minus t. Okay. Look at here. Let's check. We have to show this too. It means we have to show that I minus t times S equals I. S times I minus t is also equal to I. So I minus t times S equals I minus t, and S is this, right? Okay, sorry for interruption. I minus t and this infinite series, it means this means the limit of partial sums, right? Okay. And look at here, the product here is continuous, or more precisely jointly continuous. So this limit can go out. So this equals the limit of I minus t times sigma tk n from 0 to n. And this product equals to this, okay? And it is easy to see. Let me show you. It is easy to see. Let me show you. Okay. So now let me show you why this product equals this first. I've done it here for you. You can see I minus t times sigma t to the power of kk from 0 to n equals I minus t, and this sum equals this, right? I plus t squared up to tn. Now I times this, which is equals this, minus t times this. So look at here, t times t squared up to, and look at here the term right behind this is t to the power of n minus 1 times t becomes t to the power of n, and this time this becomes t to the power of n plus 1. And look at here, now this minus this, so t to tn, this part is gone, right? So only left I minus t to the power of n plus 1. Okay, so now you can see this product equals this, and the limit of I minus t to the power of n plus 1. Okay, the limit of I is I, but the limit of t to the power of n plus 1 is 0 operator, and then this equals I. Why the limit of t to the power of n plus 1 is 0 operator, I'm gonna explain you shortly later. And similarly, okay, this is I minus t times s, and this is s times I minus t. Similar to this, we can show that s times I minus t equals the limit of I minus t to the power of n plus 1, and the limit of this one is 0, becomes I. So you can see we have I minus t times s equals s times I minus t equals I. So this means s is the inverse of I minus t. Okay, now let me explain you why the limit of, okay, why this limit equals I. It means why the limit of t to the power of n plus 1 is 0 operator. Okay, why is it like that? You can see again, by submultiplicativity, the norm of t to the power of n plus 1 is less than, you remember just now I explained, less than the norm of t to the power of n plus 1. And let's take limit on both sides. So the limit of this one is less than the limit of this one. But look at here, the limit of this one is 0, because the norm of t is something between 0 and 1. Okay, so the limit of this one, like norm of t, is 1/2 to the power of n plus 1. So when the number is between 0 and 1, the limit of that number to the power of n plus 1, anything, when n approaches infinity, will be 0, because the number is getting smaller and smaller. Okay, so this limit 0, so this shows that the limit of the norm of t to the power of n plus 1 must be 0. Okay, and then this means actually when you say the norm of t to the power of n plus 1 converges 0, this means the norm of t to the power of n plus 1 minus 0 operator. It means we have this actually. If I show you here, this means the norm of t to the power of n plus 1 minus 0 operator. This is conversion to 0, right? So it means the distance between these two can be smaller than any positive number. So this implies that the t, okay, t to the power of n plus 1, when n approaches infinity, approaches 0 operator in b of x. So here in the limit, this will be 0, and the limit of I equals I. Okay, so that's fine. And finally, look at here, if you remember, we have to prove this, right? This inequality, finally. Look at here, for every n, Sn, which is the norm of Sn. Sn is the sequence of partial sums of this series. Again, so the norm of Sn equals the norm of, this is our Sn. This is less than, okay, from here to here we are using the triangular property of the norm. Okay, and then again, then sigma, the norm of tk, is less than sigma, the norm of t to the power of k. We have this due to submultiplicativity. Okay, you can see here. So now let's take limit on both sides. Okay, it means, look at here, from this discussion we get the norm of Sn is less than or equals sigma, the norm of t to the power of k, right? Now let's take limit on both sides. So the limit of the norm of Sn is less than the limit of sigma, the norm of tk, n approaches infinity. But look at here, this is a geometric series, right? If you remember, this is a geometric series, and the norm of t is the common ratio, and the first term is 1. Okay, so this is our geometric series, which is conversion to the first term, which is 1 divided 1 minus the common ratio, right? Okay, so the limit of this one equals this. And what about the left hand side? Look at here, since norm is continuous, this limit can go inside. So the limit of the norm of Sn equals the norm of the limit of Sn. So this limit can go inside. And the limit of Sn, which is S, okay, which is S, and that S, look at here, Sn, if you remember here. If you remember, Sn is conversion to an element like S in B of A, and S is the inverse of I minus T, right? So the limit of Sn is S. S is the inverse of I minus T. So you can see we get the norm of I minus T. Yes. So one more time I repeat. This limit goes inside. The limit of Sn is S, and S is the inverse of I minus T. So the norm of I minus T inverse less than 1 divided by 1 minus the norm of T. Okay, so this completes the proof. Okay, next we have a corollary that we just mentioned without proof because we are going to use this corollary. We need it. So just bear in mind the statement without proof. Look at here. Do you remember Bx inverse? It means the set of all invertible operators. It means the set of all invertible elements of B of X is a group, right, under multiplication, which is given by composition of operators. Okay, look at here. Do you agree with me? B of X inverse, this is easy to see that it's a subset of B of X. Okay, because this means the set of invertible elements of B of X. So this is a subset of B of X. But this, as a subset of B of X, is an open subset. Is an open subset of this. Of course, look at here. B of X is a Banach space. Okay, so it's a topological space with operator norm. So this set as a subset of this topological space is an open subset. And look at here, this map T to T inverse, okay, T to T inverse is a continuous map on Bx inverse. Okay, it means, look at here, we have a map like this. Okay, let me clear this. It means if you consider this map, we have a map from B of X inverse actually to B of X inverse. Okay, this map is given by this maps T to T inverse. Of course, look at here, when T is invertible, T inverse is also invertible. So this is an element of this one. Okay, so this Bx inverse, right, is an open subset of B of X. Okay, so if we induce the okay, what they call it, let me here write it here, and B of X inverse is a subset of B of X. Okay, so this B of X inverse with relative topology itself is a topological space, right? It means it simply this borrows the topology from B of X. So this is actually itself a topological space. So we can show that this map T to T inverse on this over B of Bx inverse, this map is a continuous map because there is a topological space, right? So we can talk about continuity. So this map, which is called inversion map, because it maps every t to its inverse, we can show that this map is continuous. Actually, it's homeomorphism because this map itself is invertible, and the inverse of this map is of the same kind. That also is continuous. So actually, this is a homeomorphism. But that's fine. You just bear in mind that this map is continuous.